Very good morning to one and all. So we are continuing the magnetic moment related issues. Now magnetic moment related things we discussed. Case 1, variation of magnetic moment due to cutting of a magnet, we completed. That is we call it as the case 1. And in case 2, variation of magnetic moment of a bar magnet due to bending of a magnet. So here the important point what we discussed in the last class is, due to bending of a magnet, there is no change in pole strength, because pole strength depends on area of cross section of a bar magnet. So but as in the case of bending, there is no change in area of cross section, so that is the reason pole strength of a bar magnet will be remains same, but magnetic length will changes. So based on that, magnetic length will decreases. Because of that, magnetic moment will decreased. Now here we completed case in case 2, point A we completed. So in this, a bar magnet is bent in the form of a shape U shape, or a shape which is looking like this. Now this is a bar magnet of magnetic pole strength M and magnetic moment M. Now the magnetic moment of this bar magnet is 2L into M. Now this is bent in the form of U shape. Now here, by keeping this S is here, we are bending the magnet like this. Now this is south pole and this is north pole of this part, and this part will be south and north, and this part will be south and north. So equally bended in the form of 3 parts. So magnetic length 2L dash will becomes 2L by 3 parts, 12 by 3. So magnet, there is no change in magnetic pole strength. So magnetic moment of each part will becomes M by 3. As we know, magnetic moment is always directed from south pole towards north pole. Now south pole to north pole, this is directed south to north, directed like this, and this magnetic moment is directed like this. So in vector notation, to identify the resultant magnetic field, we have taken like this. So this part M by 3 is acting along negative y axis minus j cap. This is along positive x axis plus I cap. This is along positive y axis plus j cap. So minus j cap and plus j cap get cancelled. The net magnetic moment will become M by 3 into I cap. So magnetic moment which is directed along positive x axis. This is point A we completed in the last class. Okay. Next, point B. Now magnetic moment, magnetic dipole is bent in the form of a shape S, or simply the shape in the following like this. This is, for example, this is north pole and this end one is south pole. So in general, a bar magnet we are taking like this. For a simple diagrammatic representation, we are taking with a straight line without drawing a magnet. Okay. Now this is magnetic dipole of this is north pole and this is south pole. Of magnetic moment is directed from south to north, and magnetic moment is M. Okay. Right. So this magnetic dipole is bent in the form of a shape S. So by keeping N is here, so we are bending like this. This S is bent like this, and it forms looking like this. Now, so this will become this is north pole. So finally this will be south pole. So now here, what is the magnetic length? So magnetic length is always a displacement which is directed from south pole towards north pole. That is the displacement which is directed from south. What is displacement? So displacement is nothing but the straight line path between initial and final position. So as it is directed from south to north, now this we call it as magnetic length. This is the magnetic length which is directed south to north. That is the magnetic length. So along direction of the magnetic length, magnetic moment will also directed. So this is yes. Now this end will act as a north pole and this end is act as a south pole, and this is north pole, this is south pole, this is north pole, this is south pole, this is north pole, and this one is south pole. So like that, because of this bending, each part of the magnet is acting as a dipole, and which is looking like this. Now, so magnetic moment is right from south to north. So south to north, south to north, south to north, south to north, and south to north. So these are the magnetic moment of each part of the magnetic dipole because of bending. So the magnet of magnetic moment M is bent in the form of like this, which is bent in the form of 5 parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That means this part M by 5, 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 and this part M by 5. M by 5. So like this we can take magnetic moment of each part. So based on the directions we can add all of them, we will get a net magnetic moment. Now, so for example, start here or here, whatever it is, we will take here this is 1. We can take this is 1, 2, 3, 4, 5. Okay. Right. So M net is equal to, this is positive x-axis I cap, plus this is positive y-axis M by 5 j cap, plus this is negative x-axis M by 5 minus I cap, plus 3 is over. Fourth one, positive y-axis M by 5 j cap, plus this is positive x-axis M by 5 I cap. Now we see M by 5 I cap, M by 5 j cap, M by 5 minus I cap. So plus I cap, minus I cap getting cancelled. So this is M by 5 j cap, this is also M by 5 j cap. Now we can write that implies M net is equal to M by 5. So 2M by 5 into j cap plus M by 5 I cap. So this is resultant magnetic moment in magnitude along with direction. Now to find magnitude, we need to find magnitude of this magnetic moment, that is M net is equal to root over. So this 2M by 5 whole square. I and J are at 90 degree. Then by using law of vector addition, we can take resultant forces equal to F1 square plus F2 square plus 2F1 F2 cos theta. So here I and J are perpendicular to each other, theta is equal to 90 degree, then this term will be equal to 0. That means F1 square plus F2 square. So this is 2M by 5 whole square plus M by 5 whole square. So this is, we will get a resultant magnetic moment. So based on the options, we need to calculate whether the magnitude along with the direction or only magnitude. So based on the situation, we need to calculate based on the options given to the question, we need to calculate either magnitude or along with the direction. Okay. So make a note of this. as magnetic moment is a vector, we can use this the law of vector addition, triangular law of vectors. Right. Next, point C. So magnet bent in the form of shape L. Shape L. Now, like this. So this is a magnet of magnetic moment M is bent in the form of shape L. Now this we can take it as north pole. This is south pole. So because of this is acting as a south pole and this is acting as a north pole. Now this is one magnet of magnetic moment M by 2 and this is M by 2. So directed south to north, south to north. Now what is the angle between these two is 90 degree. That is equal to 90 degree. Now we can write net magnetic moment will be equal to root over M by 2 whole square plus M by 2 whole square. Otherwise in vector representation M net is equal to, this is directed negative x axis. So M by 2 minus I cap plus positive y axis M by 2 plus j cap. M by 2 plus I cap. So I and j are negative y, that means negative x axis, that means negative x axis and y axis. This is negative x axis, y axis. Angle is 90 degree. So F1, 2F1, F2 cos theta, that is equal to 90 degree, the term will be equal to 0, then we can take directly like this. So this is 2 into, this is root over 2 into M by 2 whole square. Now this is root 2 into M by 2 or M by root 2. So this is the magnetic moment of a magnet is bent in the form of a shape L. A shape L. Now a bar magnet of magnetic moment is bent in the form at midpoint, which two parts of the magnet are making some angle theta. For example, like this, a bar magnet is bent. So this is midpoint. So in general, you are taking a bar magnet like this. This is south and this is north pole. Magnetic moment is directed from south to north. So having length 2L. Now as bent at middle, so this length will becomes L and this length will becomes L, which is making an angle theta. an angle theta at its midpoint. So now the angle is theta. Okay, right. Now for example, this is south pole, then this will be north pole, this is south pole, and this will be north pole. That is a north pole. Now what is the direction of the magnetic moment of each part? So this will become south to north, like this, south to north, this. Okay. Now if this is an angle, now what is the magnetic field? That means magnetic length, which is a displacement vector, which is directed from south to north. So now we can take displacement vector from south to north. So this is the direction of the effective length or magnetic length. We can take this as L effective. L. So to find to calculate this one, we will take this is an angle theta by 2. If this is some x, now sine theta is equal to opposite theta by 2. Sine theta by 2 is equal to opposite x by L. Happening this is L. Now we can take x is equal to L sine theta by 2. Now magnetic moment M dash will be equal to, so magnetic length, what is the magnetic length here? This is x and this is x. Now 2x will become magnetic length. So because of bending, there is no change in magnetic pole strength. Directly we can take it as magnetic pole strength. This will be, so 2 into, what is the value of x? X value is nothing but L sine theta by 2 into M as usual. Now this 2L into M is known as magnetic moment of original magnet. So we can write M dash is equal to 2L into M is nothing but M sine theta by 2. So this is the expression for magnetic moment when it is bent at midpoint. So by making an angle theta with the to each other. Now based on the value of theta, so theta is equal to 30 degree or 60 degree or whatever the angle we can take, and we can substitute here, then we will get corresponding magnetic moment of the bent part of the bar magnet. So this will happen only when bend is at midpoint of the bar magnet with two parts are making some angle theta with each other. So M dash is equal to M sine theta by 2. Next case. So this is a very important case. So a bar magnet bent in the form of an arc of a circle. A bar magnet bent in the form of an arc of a circle. we'll take some big one, then diagram will becomes visible. A bar magnet bent in the form of an arc of a circle. Now we can take a circular path. This is a circle of radius capital R, small r we can take. So this is the center of the circle. Now we have taken a straight bar magnet. Now this bar magnet is bent in the form of an arc of a circle. Now this is for example south pole and this is north pole. Now this bar magnet is making some angle theta at the center of the circle. This is an angle theta. Now this is radius r and this is also radius r. Now what is this? This arc length is nothing but 2L. That means length of the magnetic dipole. But what is the actual length or effective length? Or magnetic length is always a displacement vector which is directed from south pole to north pole. That means this is the magnetic length which is directed from south to north. So to find effective magnetic moment of this bent formed of the magnetic dipole, we need to calculate this effective magnetic length. So for the purpose we need to take this we can represent with y. This part we can take it as y. In the previous case how we have taken in the same way. Now this angle is half of this total angle. This will be theta by 2. So what is our aim is to calculate the magnetic length or effective magnetic length. So what is magnetic length is nothing but 2y. So 2L dash is equal to 2 into y. This is called magnetic length. So to calculate y, we can take from this angle is equal to arc by radius. That is the mathematical. In trigonometry we know angle is equal to arc by radius. So from this, what is angle theta? So theta is equal to what is arc length is nothing but magnetic length, that is 2L by what is the radius r. So from this we can say r is equal to 2L by theta. This is equation number 2. R is equal to L by theta. Now, so from this geometrical figure we can take sin theta is equal to opposite is y by hypotenuse is nothing but r. That is y is equal to r sin theta. So from this we can take it as equation number 3. From equation number 3 we can write as 2L dash is equal to 2y, which is equal to y is r sin theta. This will be equal to 2r sin theta. Okay. You note down, we will write the expression for magnetic moment. Okay. So magnetic length. So in the case of bending of a bar magnet, there is no change in magnetic pole strength. That is the reason we are not concentrating on magnetic pole strength. So there is no change in magnetic pole strength because of bending of a bar magnet, there is no change in area of cross section of the bar magnet. So area of cross section changes means there is a change in pole strength. So pole strength will be remains the same. So always we need to concentrate on how the magnetic length is changes. Magnetic length is nothing but a displacement vector which is directed from south to north pole. So by calculating magnetic length we can able to express the magnetic moment of that particular bent part of the magnet. Okay. That's the reason here we have calculated magnetic length is 2r sin theta. magnetic moment m dash is equal to 2l dash into m. What is 2l dash? Is nothing but 2r sin theta. 2r sin, this is theta by 2 na, sin theta by 2, sin theta by 2, this is sin theta by 2, this is sin theta by 2. So 2r sin theta by 2, not this only we have taken. Sin theta by 2 is equal to y. Sin theta is equal to y by r. So r is equal to, or y is equal to r sin theta by 2. 12 dash is equal to 2r sin theta by 2 into m is as usual, which is equal to, what is the value of r? So from this equation number 2 we can write r is equal to 2l by theta. This is 2 into 2l by theta into m into sin theta by 2. Now in the place of this 2l into m, this is nothing but magnetic moment of original magnet before bending. So m dash is equal to 2 into, this is m, 2m sin theta by 2 by theta. So this is the expression for magnetic moment of this bent part of an arc of a bar magnet. So it's bent in the form of arc of a circle. So here theta must be in radian. Theta must be in radian. So for example, a bar magnet is bent in the form of semicircle. So bar magnet bent in the form of semicircular shape. Then what is the magnetic moment? M dash is equal to 2m. So semicircle means like this. So what is the angle this is making at the center is, so why you are taking center? While calculating you are taking theta is angle suspended by ends of the bar magnets, at its center. Theta is the angle made by ends of a bar magnet at the center of the circle. Now, as it is as bent in the form of semicircle, this is one end of the bar magnet and this is another end of the bar magnet. So which is making an angle at the center like this. So this is 180 degree or pi radian. Now, so 2m, so pi is 180 by 2, that is sin 90, we can take it as 1, sin 90, 1. So by what is the value of theta? Is nothing but pi. So 2m by 5. So this is the expression for magnetic moment of a bar magnet which is bent in the form of semicircular shape. M dash is equal to m by pi. So like that, whatever may be the angle. So theta is equal to 60 degree. Now another example, if a bar magnet is bent in the form of an arc of a circle which is making an angle 60 at the center. Now m dash is equal to 2m sin 60 by 2, sin 30 by theta. 60 means, so 180 by 60. That means pi. Pi is nothing but 180. That means this is pi by 3 radians. So this will be pi by 3 radian. 180 by 3 means 60. 180 by 3, 60 degrees. Pi by 3 radian. Now sin 30, 1 by 2. 1 by 2, 2 will cancel. This m dash is equal to 3m by pi. To m sin 30 1 by 2, 2 will cancel. This is pi by 3, 3 will go upside, 3m by 5. This is a previous NEET question. The angle 60 degree. They asked a question in 2013 NEET examination something. We'll see the numericals, then we can get in which year they asked this question. Okay. Like that with 60, 30, they may ask the question on bending of a bar magnet. So bar magnet is bent in the form of semicircular, means m dash is equal to m by pi. It is bent in the form of an arc of a circle which is making 60 degree at its center. Is m dash is equal to 3m by pi. 3m by pi. So this arc of a circle is very important case. Next point. Okay. Now here when bar magnet is bent in the form of semicircle, magnetic moment will be 2m by pi. Okay, right. So this is south pole and this is north pole. Now in this case we are taking a bar magnet. We are bending half of the part of the bar magnet. Half of the part of the bar magnet. That means when I am taking half of the bar magnet, this magnetic moment will be m by 2. This magnetic moment will be m by 2. Now without disturbing this half part, we are bending only this remaining half part. That means by keeping this part remains the same. This is north pole, remains the same. Now this part only is bent in the form of a semicircle. Bent in the form of semicircle. Now what happened? So this will becomes, this is north, this is south. Again this will becomes north pole and this will become south pole. Now what is the value of magnetic moment of this part is m dash is equal to, in the form of semicircle, so 2 into 2m by pi. In general, magnetic moment, magnet is bent in the form of semicircle 2m by pi. But what we are taking only half part of the magnet only is bent in the form of semicircle. That means in the place of m, what we need to take? We need to take this m by 2. M by 2 by pi. This will be equal to m by pi. So this is very important case. With simple logic we need to take this value m by pi and 2m by pi. In general, in this case, we have taken entire magnet of magnetic moment m is bent in the form of semicircle. So by using this equation, we have calculated m dash is equal to m by pi. But in this case, what we are taking? We are taking part of the wire, part of the bar magnet. It is bent in the form of semicircle. So m by 2 is bent in the form of semicircle. That is the reason we have taken m by 2 by this one. Otherwise, if you taken like this, what is the magnetic moment? So of this part will be m by pi. What is the net magnetic moment of this part? So to calculate net magnetic moment, we need to identify the direction. This part magnetic moment is directed south to north like this. Again, so as this is north pole, this is south pole, this bar magnetic moment is also acting like this. Now both are along the same direction. So what is the net magnetic moment? So net magnetic moment will be equal to root over m by pi whole square. No, directly we can add, na? Both are in the same direction. So m by pi plus m by 2. M by plus m by 2, because both are in the same direction. We can add directly. This part magnetic moment is m by pi, this part magnetic moment is m by 2. So directly we can add because both are directed in the same direction. But in some other cases, this bent part of the bar magnet, this is north pole, south pole, magnetic moment m by 2 directed like this. Okay. Now this bent part of the magnet is placed like this. Is bented like this, and the bent part is again bent in the form of like this, vertical to the point. Now this is north pole, means this will be south pole. Again this will be north pole. It is directed in this direction. Now what is the magnetic moment of this magnetic moment of this part direct from south to north? That means like this. So what is the angle between these two magnetic moments? 90 degree. So 90 degree means this part net magnetic moment will becomes m net is equal to root over m by pi whole square plus m by 2 whole square plus 2 m by pi m by 2 into cos 90 degree. That part will becomes 0. This is magnetic moment of a bar magnet is bent in the form of like this. Okay. So to confuse us, they will ask this type of question. Okay. Right. Okay. So this is about variation of magnetic moment due to bending of a bar magnet. Bending of bar magnet. This is case 2. Now case 3. Variation of, or we can keep like this, resultant magnetic moment, due to combination of magnets or bar magnets. Resultant magnetic moment due to combination of bar magnets. So here, what are the points or what are the cases we are discussing? Those cases or those points are directed numericals. So with the help of these cases, directly those cases they will ask as a numerical, and otherwise they will give magnetic moment. For example, in this case, they will give maximum moment of entire bar magnet, they will give magnetic moment. So that maximum moment value simply we need to substitute here, then you will get effective magnetic moment or net magnetic moment. Okay, so by simply giving by these values, they will ask the numericals. Otherwise, directly these expressions they will ask in the examinations. Okay, so that is the reason here there is no need of specially concentration on numericals. So you can able to solve the numericals, because directly they will ask direct formula. Otherwise, if they want to ask numericals, means they will give magnetic moment, initial magnetic moment value. So later after what is the net magnetic moment or part of the bent part of the magnetic moment, they will ask. So numericals, I will send a file so you can practice the numericals based on this. So otherwise, those direct cases also can be treated as numericals. Okay, right. So resultant magnetic moment due to combination of bar magnets. Now point A. Now here two bar magnets we are taking like this. So this is of one bar magnet. And another bar magnet we are placing like this at some angle. Now this is south pole and this is north pole. This is south pole and this is north pole. So these are identical bar magnets. We are taking identical bar magnets. So the magnetic moment of this one is M and this one is also M. Now direction of this magnetic moment is directed like this. So we can take M1, M2. Later we can apply for identical bar magnets. Now, so what is the direction of the magnetic moment of this magnet is from south to north. Again, direction of magnetic moment of this magnet is also direct from south to north. So by extending these 2 points, we can say the angle between these 2 magnetic moments will be equal to theta. Now by using law of vector addition or triangular law of vectors, we can calculate net magnetic moment. So net magnetic moment is equal to root over m1 square plus m2 square plus 2m1 m2 cos theta. So this is the expression for magnetic moment of 2 bar magnets which are making an angle theta with each other, will be like this. Okay, by using this equation we can calculate. So if theta is equal to 30 degree, theta is equal to 45 degree, or theta is equal to 60 degree, they will give. Okay. So based on this case, they asked in NEET examination, they asked previous questions. They given like this with theta is equal to 45, theta is equal to 30, theta is equal to 60, like that. They given 4 diagrams. So by seeing both 3 diagrams, in which combination, in which arrangement magnetic moment is maximum. Magnetic moment is maximum. So that is the question they asked in previous examination. I will show that question once. Yes, this is the question they asked based on that point. In 2014 AEMT, they asked this question. So following figures show the arrangement of a bar magnets in different configuration. Each magnet has magnetic moment of M, identical bar magnets. Identical bar magnets. So which of the following has highest net magnetic moment? Net magnetic moment. So here angle is 90 degree. So here angle is south to north like this, south to north like this. Both are in opposite direction. So net magnetic will be equal to 0. Now here 30 degree and here 60 degree. So by using that root over m1 square plus m2 square plus 2m1 m2 cos theta, cos 30, cos 60, cos 90, this is 0. So we can cancel this one. So we can be able to find cos 30 means something greater than this one. Out of these 2 we can go with 30. So cos 30 root 3 by 2, cos 60 1 by 2. That's the reason 2 will cancel, here root 3 extra will come. That's the reason in this case magnetic moment is maximum. So by using that equation we can calculate resultant magnetic moment in all the 4 options, and we can find in which option magnetic moment is maximum. Okay. Next, point B. For example, bar magnets are arranged like this in the same arrangement by changing poles of the magnet. Okay, see this. So here this is south pole and this is north pole. Now here we need to take this as north pole and this is south pole. So in the previous case this is taken as south pole. Now we are changing polarity of a poles of a bar magnet. Now magnetic moment of this part is M1. We can take this is M1 and this is M2, which is direct from south to north in this direction. Now this is directed like this. South to north. So magnetic momentum is a vector quantity. So how can we find the angle between the two vectors? So angle between two vectors is angle between tails of two vectors. Tails of the, for example, these are the two vectors like this. Now this is not the angle between the two. So now we need to take this is the vector. This is the vector. Now the tail of this vector we need to imagine here. We need to imagine vector like this. Now the angle between these two is this one. This is the angle between two vectors. So while finding angle between two vectors, always we need to take the angle between the tails of the vectors. Tails of the vector. That is the point we need to consider. So here, so that is the reason in this case, in the first case, so this is tail of a vector and this is also tail of a vector. So angle between them is theta. Now here in this case, if you are extending this magnetic moment like this is M2. Now what is M1? This is M1. This is M1. Now this will be angle between these two. That means this will be 180 minus theta if you are taken this as theta. That is theta. Now we can take M net is equal to root over M1 square plus M2 square plus 2 M1 M2 cos 180 minus theta. So cos 180 minus theta minus cos theta. So minus 2 M1 M2 cos theta. So this is the expression for magnetic moment in this case. So simply as we changed poles of a bar magnet, the expression has changed. Okay. This is plus 2 M1 M2 cos theta, tail and tail. Now here as reverse because of that, so it came minus because of this angle 180 minus theta. So always we need to find the angle between two tails of a vector. So while calculating numerical, we need to identify direction of the magnetic moments or poles of the magnets. We need to clearly identify. Then only according to that we need to take the angle between two magnetic moments of two bar magnets. Right. Point C. This is one bar magnet. And we are placing another bar magnet like this. This is of M1 and this is of M2. Okay. Otherwise, we will simplify. This is one bar magnet above which we are placing another magnet. South pole, north pole, south pole, north pole. Now, what is the magnetic moment? M1 is directed like this, M2 is also directed like this. Again, this is south pole, north pole, this is south pole, north pole. M1 is directed like this, M2 is also directed like this. Now, net magnetic moment in these two cases will be M1 plus M2. M1 plus M2. In the same way, we can take another two bar magnets which are arranged like this. This is south pole and this is north pole. This is north pole and this is south pole. Now magnetic moment is directed like this and this magnetic moment is like this. This is M1 and this is M2. The same way, we have taken two bar magnets which are placed in this manner, directed in this manner, M1, and this is south and this is north. Now this is north and this is south, directed like this. Now in this case, net magnetic moment will be M1 minus M2. If M1 is greater than M2, M is greater than M2. So M net is equal to 0. M net is equal to 0 when if M1 is equal to M2 is equal to M2. So based on the linear arrangement or one above the other, when magnets are placed like this, we can calculate net magnetic moment by identifying direction of the magnetic moments. So M1 plus M2 or M1 minus M2. So if they are identical, here magnetic moment will becomes M plus M to M. So here magnetic moment will becomes 0. Next point. For example, identical bar magnets, identical bar magnets are arranged as sides of equilateral triangle. Identical bar magnets are arranged as sides of equilateral triangle. Now here, first bar magnet like this, second bar magnet like this, and third magnet like this. So this is M, this is M, and this is M. So by taking direction, we can identify south and north pole. This is south pole and this is north pole. South, north, south, north. That means we can take this as this is south, and this is north, this is south, this is north, this is south, and this is north. So while giving the question, they will give identical bar magnets are arranged as the sides of equilateral triangle such that opposite poles are at the corners of a triangle. Opposite poles are at corners. Then, as according to triangular law of vectors, if two vectors are representing two sides of a triangle in the same order, the resultant of these two vectors is another or third side of a triangle which is in opposite order. So now if this is A, this is B, then this is resultant vector will be R is equal to A plus B. So this is the statement of triangular law of vectors. If two vectors are representing two sides of a triangle in the same order, then the resultant of these two vectors is a third side of a triangle which is in opposite order. Then only this will become a resultant of these two vectors. But one direction of this is reversed. If it is in the same order, that means net value will be equal to 0. So in the same way, so it has all are in the same order. Now the net magnetic moment of this arrangement will be equal to 0 because effective magnetic length is equal to 0. So from that point we can say net magnetic moment is equal to 0. Otherwise we can take like this from the statement of triangular law of vectors. So based on this, in 2019 they asked the question from the chapter of laws of motion. They given forces. This is force F, and this is force F, and this is force F. So three forces are acting at a point as shown in the figure. Then what is the motion of the body? So as the three forces are acting like this means resultant force will be equal to 0. That means MA is equal to 0. That means A is equal to 0. That means velocity is constant. Acceleration 0 means acceleration is nothing but dv by dt. So dv by dt is equal to 0. That means velocity is equal to constant. So velocity constant means this is the motion of uniform motion. So in the given options they given uniform motion, accelerated motion, decelerated motion, like that they given options. So as from this statement of triangular law of vectors, net force will be equal to 0, then acceleration is equal to 0, velocity is constant. That means particle is in the state of uniform motion. So like that we can calculate net magnetic moment is equal to 0. In the same way, if four magnets are arranged to form a square at opposite poles are at corners, south, north, south, north, south, north, south, north. Now again these two are in opposite direction, so the net magnetic moment will be equal to 0. Okay, so identical bar magnets are arranged in the form of sides of equilateral triangle or square with the opposite poles are at corners of a triangular square. Then net magnetic moment will be equal to 0. Next case. Okay. For example, three magnets of different magnetic moments are arranged as the sides of three sides of equilateral triangle in the same order. Now this is of magnum moment m, this is of magnum moment 2m, and this is of magnum moment 3m. Now what is the magnum moment of net magnum moment of this combination? So we need to find. So these are sides of an equilateral triangle. Now as usual, this is south pole, north pole, south, north, south, north. Now this we can equivalent to, we can take this is m, this is m, and this is m. So from this magnum moment m, from this magnum moment m, from this magnum moment m we have taken. That means 3m means this is resultant of 3 identical bar magnets. Now out of these 3 we have placed one magnet is like this, one magnet is like this. So because of this part, magnum moment will be equal to 0 plus. So this is m already taken, there is no magnet here. Now here already m is taken means remaining m will be acting like this. Bar magnet of magnum moment m is acting like this. So in this direction, magnum moment already m is removed for this. Next 2m is acting like this. Now what is the angle between these two? Angle between the vectors will be angle between tails of the vectors. Now we need to extend this one, like this is m. This is the tail of this vector. Now the angle between these two is like this. As we are saying, this is an equilateral triangle. This angle is 60 degree. Now this angle is 120 degree. Now net magnetic moment of this combination will be equal to root over m1 is m square plus 2m whole square plus 2 into m1 m2 cos 120. So what is the value of cos 120 is 1 by 2. So we can simplify, then we will get net magnetic moment. This is how we need to calculate net magnetic moment. So by simplifying, we can take by taking this is, for example, this is 2m. For example, this is 2m. This is 2m. This is 3m. That means 2m will get cancelled. The resultant will be m only. So like that we can simplify. In the same way, they will give in the form of a square. So in the form of square also we can use the same technique to calculate resultant magnetic moment. So these are all related to numericals. So we are indirectly solving numericals also. Simultaneously we are solving numerical. Like that we need to consider. Okay. Now identical magnets are arranged like this. For example, this is one magnet, one bar magnet, a magnet moment m. So another magnet is placed like this. This is third one. So magnets are arranged like this. This is of magnetic moment M. All are identical. All are identical. Now to calculate the effective magnetic moment of this arrangement of 6 magnetic dipoles, we need to take this one, and this one are along the same direction. So we can add directly. So this we can simplify with like this. This is of magnetic moment 3m. Like this we can take, and this one and this one and this one are at same. So we can add this also same. This is of 3m. That is of 3m. Now they will give angle. For example, this is 60 degree. That is a 60 degree. Now what is the angle between the vectors? Angle between the vector is nothing but angle between tails of the vector. So this is tail of this vector. We need to extend this vector like this. Now they will give this angle. This is 60 degree. But what is the actual value we need to take? So we need to take actually the reading of the angle between tails of this vector. This is 120 degree. 120 degree. Now net magnetic moment will be equal to root over 3m whole square plus 3m whole square plus 2 into 3m whole square into cos 120 degree. So this is how we can calculate the net magnetic moment of this arrangement. So how we are splitted? So 2m, 3m into m, 3m is m and 2m. How we splitted these magnetic moments? In the same way, we need to add magnetic moments of all these. So when all are in the same direction, so same directed magnetic moment we can add directly. Correct. So 3m is acting like this, and if third magnet is not there, this is not there, means m, 3m, m and m, 2m. So m and 2m are at 120 degree. So we can take 120 degree and calculate the numerics. Okay. So this is how we need to calculate the resultant magnetic moment of different arrangement of magnetic moment or different combination of magnetic dipoles and its effective or resultant magnetic moment. So with this, the concept of magnetic moment completed. So regarding magnetic moment, we discussed three important cases, because variation of magnetic moment due to cutting of a bar magnet, and second one is variation of magnetic moment due to bending of a bar magnet, and third one is variation of resultant magnetic moment due to combination of the bar magnets. So with this, the concepts related to bar magnets completed. Okay. Now we will see some numericals on magnetic moment. Okay, this we already discussed. This is south to north like this, south to north like this, angle is 90 degree. South to north, angle is magnetic moment is 0. This is 30. So root over m square plus 2m square cos 30. Cos 30 root 3 by 2. So here cos 60 1 by 2. So root 3 by 2 1 by 2. So root 3 by 2 is greater than 1 by 2. So then we can go with option 3. Okay. Right. That is previous question. Okay. In 2013 they asked this question. A bar magnet of length L and magnetic dipole moment M is bent in the form of an arc as shown in the figure. The new magnetic dipole moment will be, now new magnetic moment M dash is equal to 2m sine theta by 2 by theta. Now this is 2m into sine theta by 2. Theta is 60 degree. What is theta? The angle suspended by ends of the bar magnet at its center. Angle suspended by ends of a bar magnet at its center is nothing but theta. This is 60 degree sine 30. So 1 by 2 by, so theta must be represented in radians. So in radians 60 degree we can represent with pi by 3. So now, so this 2 will get cancelled, 3 will come outside. This is 3m by pi. 3m by, here is the, so here one more point I forgot to give that point. You see, you write this point. If a bar magnet, in the form of an arc is straightened. So this is the case, bar magnet is bent in the form of an arc. Now bent form of bar magnet is now straightening. Then how we need to find the magnetic moment of this straightened part? That is m dash is equal to m theta by 2 sine theta by 2. This is the formula to calculate magnetic moment in the case of straightened. So this theta will go upside, so this 2 sine theta will come down. So like that we can remember the formula. When bented magnet is straightened, then to calculate the magnetic moment of that straightened part of the magnetic dipole, we can use this formula, that is m dash is equal to m theta by 2 into sine theta by 2, where theta must be in radian. Okay, you note this point. Now this already we discussed. A steel wire has magnitude m, it is bent into semicircle. The new magnetic moment will be, that is cos 180 degree. Semicircle means 180 degree pi, then 2m sin 91, so 2m by pi. This also we discussed. A bar magnet of pole strength m and magnetic moment m cut into two pieces along its axis. So when we are cutting along its axis is nothing but a straight line which is extended to the south and north pole. This is called axis of a dipole. Now cutting is along the axis. Like this we are cutting a bar magnet. Because of this, area of cross section became half. This piece magnetic length is 2L. This piece magnetic moment is also, magnetic length is also 2L. So because of change in area of cross section, pole strength will change as m by 2. Pole strength of this bar magnet will becomes m by 2. That means magnetic length, there is no change in magnetic length, but pole strength will becomes m by 2. Now the new magnetic moment of each part will becomes m dash is equal to 2L dash into m dash. So here new magnetic length is remains the same, that is 2L into magnetic moment, magnetic pole strength will becomes m by 2. This is m by 2. So 2L m is nothing but original magnetic moment by 2. So magnetic moment will becomes m by 2, and pole strength also will becomes m by 2. So the magnet of pole strength m and magnetic moment m is cut into two pieces along its axis. Its pole strength and magnetic moment. So pole strength will becomes m by 2. Magnetic moment is also will becomes m by 2. But there is no change in magnetic length. So in AFMC they asked this question. Okay, this model we already discussed. Bent in the form of, half of the part is bent in the form of semicircle. As a case, as a point we discussed this one. Okay. This is also same. These are all we discussed in the form of cases. Okay. See how they will answer the question based on this. A magnetized wire of magnetic moment. So magnetic moment is given 1.57 into 1.57 ampere meter square. Bent in the form of a semicircle. The new magnetic moment will be. So new magnetic moment already calculated. That is m dash is equal to 2m by pi. Simply they given m is equal to 1.57. This is 1.57. Pi value you can take it as 3.14. So we can simplify the mathematical equation. We can get the value of new magnetic moment. So like that simple, by giving magnetic moment value they will ask the questions. Okay. That is one. Okay. So this is how we can calculate. You see this? This is one magnet and this is another magnet. This is one magnet and this is another magnet. So this M and this M are along the same. Thus we can write it as like this with magnetic moment M. This is M and this is also M. Now resultant of these two will be 2M. Resultant of these two also will be 2M. Now what is the angle between these two? The angle between these two is given like this. But we can't take this 60 degree directly. What is the angle? Angle is the angle between two tails of the vector. So that is the reason we need to extend this vector like this. And this is 2m and this is 2m. Now this is the angle. So angle is 120 degree. So to confuse us, they given this 60 degree here. But we can't take 60 degree directly because angle between two vectors is always angle between tails of the vectors. So that is the reason now we can able to apply. So root over m1 square plus m2 square plus 2m1 m2 cos theta. So cos 120 degree. Cos 120 degree we need to take. So cos 120 degree is minus 1 by 2. Minus 1 by 2. So like that we can take, and this is they taken 60 but they will taken minus. What is the reason? What is the reason we have taken? So 180 minus theta. 180 minus theta we have taken. So this is theta value 180 minus theta is taken and he has calculated minus. Otherwise if you are taking 120 degree means directly we will get the answer. Okay. Right. This is in the form of U shape we already discussed. S shape, this is also we discussed as a case. Okay. Now here the two magnets are like this, which is making an angle theta. So this is based on resolution of the vectors. This is making an angle M like this. This will be this is vector. Vector can be resolved into two components. So this is one component like this, and this is another component. This is M cos 60 degree. This is M sin 60 degree. Now in this direction resultant will be M plus M cos 60 sin 30 1 by 2 cos 60 1 by 2. So M by 2. So in this direction M by 2. Now this is M sin 60. M sin 60 is nothing but M into root 3 by 2. It is acting in this direction. This is M is acting upward direction. That means resultant of in this direction. That means this is M. This is root 3 M by 2. Resultant will be in downward direction. So what is the resultant? Root 3 M by 2 minus M. Minus M. So this resultant is acting is in this direction. M plus M by 2 is acting in this direction. Root 3 M by 2 minus M is acting in this direction. Both are at 90 degrees. So now we can apply root over m1 square plus m2 square. Otherwise has taken like this. So first he has calculated 2. So first in this method what they did is, first he has calculated m and m acting at 60 degree. Resultant he got root 3m. Now root 3m and m are at 90 degree. So like this they calculated the values. Okay. So in this manner we can calculate, and in this way also we can calculate. So whichever is comfortable for you, that method you can adopt. Okay, I will send this file to you. you can practice these numericals. Okay, in the form of square we already discussed, in the form of triangle we need to discuss, we are already discussed as a cases. Okay. So these are all the points or numericals related to magnetic dipole moment. Okay, these are all because of cutting of magnets and it's a magnetic moment. Now see this question. If a bar magnet is cut into 4 times parallel to its axis line. So 4 times parallel to its axis line means, parallel to means m dash will becomes m by 4. 2l dash will becomes 2l. There is no change in length. So pole strength will becomes m by 4 because of this parallel cutting. Okay, right. 4 times perpendicular to its axial line. Perpendicular cutting, what happened? 2l dash is equal to 2l by 4. M dash is equal to m. In vertical cutting, there is no change in magnetic pole strength. Now we need to find net magnetic moment. So in this case, because of parallel cutting, pole strength will becomes m by 4. Because of perpendicular cutting, magnetic length will becomes 12 by 4. So m dash is equal to m by 4. 2l dash is equal to 2l by 4. Right. If a bar magnet of pole strength m and magnet moment m is cut equally 5 times parallel to its axis. So parallel to axis means m dash is equal to m by 5. So 2l dash is equal to 2l. There is no change. Now 4 times perpendicular to its axis. That means now 2l dash will becomes 2l by 4. M dash will becomes m. Now what is the net magnetic moment? M dash is equal to 2l dash into m dash. What is 2l dash? 2l by 4. What is m dash? M by 5. That means 2l into m is nothing but original magnetic moment. 4 into 5, 20. So that will be equal to m by 20. So parallel cutting, there is a change in area of cross section. Because of that area of cross section changes, there is a change in pole strength. In perpendicular cutting, there is a change in magnetic length. So because of that magnetic length, magnetic moment will changes. So whatever may be parallel cutting or perpendicular cutting, pole strength and magnetic lengths are differently changes, but magnetic moment will be changes according to that pole strength and magnetic length. So this is about the magnetic moment of a bar magnet. So with this we completed magnetic moment related cases and numericals. Okay. So in tomorrow class we will discuss about magnetic field due to isolated magnetic poles and also magnetic field due to magnetic dipole. Okay, thank you.